Hello, I'm Sumit Bose, founder of Future Net Zero. We are a website that produces content to help you cut your carbon footprint. And the Net Hero podcast is all about that, highlighting people doing amazing things to cut emissions, be that scientists, business people, inventors, or just common, ordinary people who are doing something to make a change. If you want to get involved, then email us. And we're looking for a sponsor for this amazing podcast. So if you'd like to know more, get in touch. On to this week's episode. This I'm looking forward to, and you should be too. Now, you've known, if you've been listening and watching my podcast for years, I'm a bit of a science fiction man. And I have a utopian dream, perhaps because when I grew up in the 70s and 80s, sci-fi was massive. And the idea is that you'd have clean energy. Nearly every science fiction book or, future scenario, whether it's Star Trek, Star Wars, whatever, they don't talk about pollution because they've got clean energy and they've got faster than light travel and all these weird things, and they've cracked the thing that does the existence of our lives. Fusion power. What is it? Is it real? It's a thing that powers the sun, but will it really power our future? It's been one of those things that's been trapped in the pages or on the screen in sci-fi. But could it now be a reality? I know what you're thinking. It's 30, 40 years ago. That's what everyone says. And I've had people on the podcast saying it'll never happen. But has something shifted? Has the creation of artificial intelligence made fusion a reality that isn't a dream, but a reality in a very short term? We've seen small examples of fusion. You may have read stuff over the last few years about people finding the way to actually put the atoms together. But what will we actually get to the stage where we do have that clean power? That's what I'm going to discuss today. And I'm delighted to say I'm joined by Sahila Gonzalez from the Clean Air Task Force, who's also a physicist, who's also just come back from COP, who also is going to be our fusion guide. So, buenos dias.
Buenos dias. Glad to be here.
Glad to have you. And I know that you're in Spain and it's sunny, but we'll discuss a little about that later. Let's start with that. I mean, I've given a sort of idiot's guide to fusion, but in reality, for our listeners, what is fusion?
Well, fusion is a quite simple thing. First thing, as you mentioned, fusion is happening every day because every second the sun, the stars are powered by fusion. So it's nothing strange to us.
It's a natural thing.
It's a natural thing.
Yeah.
The problem is to replicate that on Earth because the conditions to reach fusion, to make nucleus to fuse, are extreme. You need extreme temperature. You need to have all the nucleus close to each other, confined, and you need to keep that conditions for long enough. So we are trying to develop a machine that meet all these conditions, to have enough temperature, to keep the nucleus close enough, and to make it for long enough. Which kind of nucleus are you talking about? Which is these elements? It's nothing strange. It's hydrogen isotope. So deuterium and tritium is the usual fuel that you use for the fusion machines because it's the easiest reaction to achieve on Earth. As simple as that. We go for the easiest one. So the only thing that you need to do is to fuse together these two nucleus. By fusing, they will release energy by this famous equation of Einstein, E equal mc squared. And that energy you need to capture and make it available to the grid. It sounds easy, but the technology associated to that is complex.
It's two hydrogens, right? And it's two hydrogens.
It's two hydrogens. Two hydrogens that they need to collide each other. And for that, you need to create a plasma. And to create a plasma and sustain a plasma at high temperature, you need to create a device. The most advanced device is a tokamak. This is where the confinement, this is called confinement, is higher. But there are other concepts like accelerators, like linear concepts, and now with the new technologies and the new options that we have are becoming also popular, let's say, they are being studied, and each of one has convenient features and not so convenient. So we are opening our options to find the best of each of these devices to see which one will win the race that at the end of the day, we all want to have fusion delivered as soon as possible.
We'll explore that in a minute, but I've always heard the term plasma, and I don't understand what it is. So what exactly is a plasma?
A plasma is a popular thing. It's nothing strange. You have in many bubbles and in many applications. It's the fourth stage of the matter, and it's when you heat up a gas enough to separate the negative charge from the positive charge. So in this case, you separate the nucleus that is a positive charge with protons from the electrons that is a negative charge. And in that plasma, and it's hot gas, you move them and you make them to collide, to fuse. And you need to keep all these confined. And how do you confine all this plasma? With magnets, because the magnets can decide a charge particle trajectory. So the way to drive these charge particles is through magnets, through a magnetic field. This is why the fusion machines, the magnetic ones at least, are based on magnets, because you need these magnets to produce a magnetic field and to confine all these particles.
Is that what happens in the sun? So the sun basically is taking hydrogen and it's squishing it together. Does it produce helium, or is it just, how does it work in the sun?
The nature is more advanced than the human being, which is an important point. Yeah. And the sun doesn't have any magnets. They have a better thing, which is gravity. So the replacement of the
sun is massive. Right.
Yes, massive. So we cannot have this gravity effect on the Earth. So we need to simulate it, let's say, with the magnet. So in the sun, first of all, you have a deuterium-deuterium reaction, and you make this confinement trans to the gravity. And then you have the fusion reaction, you have the release of energy, you have the release of helium, and so on.
And is that what basically makes the sun glow and makes the heat?
Yeah.
Simple as that.
That is, fusion is powering the stars, the sun in particular, because the heat that we receive on Earth is coming from fusion of deuterium produced in the sun.
Why is it that fusion has always been seen as this clean power? Like I said, my youth, science fiction novels. It's what's the difference between, and I know this is taking you right back to your school days, but for my audience and for me, what's the difference between the nuclear power we have now, which is called fission, and fusion? And what is the difference in terms of the energy?
Honestly, fusion and fission are basically the opposite, because in fusion, you have two light elements, hydrogen isotopes, that fuse together and release energy, because the Einstein equation. And to do that, you need a type of machine that you are able to have this high temperature and confine with magnets and so on. So in a fission reaction, you have the opposite. You have a heavy nucleus, a heavy element like uranium and plutonium, where what you do is with a neutron, you kick off, let's say, that nucleus, and you split it into pieces.
Yeah.
And because you split it, you generate more neutrons, and these more neutrons can split it more uranium or plutonium, and so on. And this is called chain reaction.
Right.
And what you need to do in your fission reactor, among other things, is to control this fission, this chain reaction. This is why the safety aspects are so important. In fusion, you don't have this chain reaction. The difficult thing in fusion is to keep the reaction, the plasma, in the good conditions to be able to produce fusion. So this is why people always say fusion is inherently safe, because you don't have this chain reaction. The worst thing that can happen in a fusion machine is that they shut down. Okay, fine.
So it's safer. That is the main thing.
This is a key feature of fusion. The second thing is, since in a fusion machine you are going to have hydrogen isotopes, you are not going to deal with uranium, plutonium, fission products, and all these highly activated elements that you end up having high-level rad waste. So having to handle rad waste for thousands of years. In fusion, the lifetime of tritium, which is one of the isotopes of hydrogen, is 12 years and a half, more or less.
Right.
And then it is true that you have a neutron of 14 MeV, and you can activate materials surrounding the walls of your machine.
Yeah.
But that materials are made in a way that after 100 years can be reused or recycled.
So is there? We know about radiation in fission. So you're saying there is some sort of radiation in fusion as well, but it's a lot shorter.
There is sort of radiation in fusion too, but you are comparing 10 years with thousands of years, and the level of activity is completely different. Like when you go to the hospital and you go and you have some treatment and you have some radiation, and the radioactivity lasts for 2 hours, 3 hours, even 50 minutes. Cannot compare.
Gotcha. And the other thing is, I suppose, the base material for all our fission reactors is things like uranium and plutonium. They're heavy, they're radioactive to begin, all of that sort of stuff. Will we just, before we explore what you're doing, but just going back to the fundamentals, with fusion, would you just take hydrogen gas and that's what you use?
In fusion, to fuse things, you need very light elements, and the lightest element is hydrogen. So what you use is hydrogen, mostly hydrogen, and isotope of hydrogen. So tritium, deuterium is not radioactive. Tritium is radioactive, but the lifetime of tritium is 12 years and a half. It's something that we can handle in much easier way than uranium or plutonium. So because the needs are completely different. In one case, you need a light atom, and in the other case, you need a heavy atom. So it's the opposite.
We've always had this idea that the problem with fusion is that, and again, you're the expert, but it takes so much energy on Earth to make the fusion. It's not worth it because you're putting more energy in than you're getting out. Or is that wrong? Or has it been just we just can't do it?
Well, this is not wrong. This is the R&D that we are following to reach a commercial source of energy. In a commercial source of energy, you need to be Q higher than 1, higher than 5, higher than 10. And Q is the gain that you have. So you need to extract more than you put. So when you read something about fusion, you say Q equal 1, Q higher than that. So this is your gain. This is a key number that you need to remember. So the first time that it was proved on Earth that we have a Q experimental higher than 1 was a couple of years ago by Lawrence Livermore Lab, Lawrence Livermore National Lab. So it's true, we are able to do it. We are able to have this gain, at least an experimental gain on fusion.
So hang on, this is a very important point. We can do fusion at present on Earth.
We can do it, and we have done. And then after that experiment in Lawrence Livermore National Lab, they have replicated even more successfully. So it's a reality.
Wow.
And that gives confidence to investors, for example. So what is happening right now? That to have this Q higher than 1, Q higher than 5, Q eventually higher than 10, we need to improve our technology. And this is what we are doing right now. We are improving the technology, focus on a commercial way. We are not any longer focusing on R&D. That is important. It was a phase. You have to take into account the R&D on fusion. Fusion was discovered or understood because it was existing last century in the 20s.
Yes.
So all these periods have been R&D, which is needed. So the scientific progress was huge, but not the technological progress. And now this technological progress is coming together with a focus on commercialization.
So you're, sorry to stop you there, but what you're saying is that since we've known about how the sun works, it's all been science in the lab trying to prove the way it works. We then got to this stage a few years ago where they actually made it happen, that they got an energy gain. So again, I don't want to put words in your mouth. Have we reached the point where the science is now proved and all it is making this process more efficient and bigger? Is that where we're at?
This is exactly where we are around. And if I may add a couple of things on that, this is happening now because we have enough or quite substantial scientific knowledge. But in addition to that, we have a number of enabling technologies that are making fusion possible from the commercial point of view. For example, a few years ago at MIT, they proved that they could build high temperature, high field superconducting magnets and reach 20 Tesla. If you are able to have these 20 Tesla with these magnets, that makes your machine much cheaper, much faster, much easier to build. That changed the whole equation. That changed the whole thing.
What's 20 Tesla? What does that mean?
20 Tesla is the magnetic field. As we were talking before, you need a magnetic field to confine your plasma. So until this 20 Tesla, you were building coils with superconducting materials, even before with copper, just conducting materials that provide you only a few Teslas.
This 20 is a magical figure where the field is strong enough.
Right now, we can build machine with up to 20 Tesla and even higher, which since you have a much stronger magnetic field, you don't need to make such a big machine. You can make it cheap, smaller, and smaller means cheaper, and it means faster. So without this technology, we will not be able to even think about this commercial viable fusion. Now you have this element, and that changed the whole equation, because now you know how to make that machines easier, cheaper, faster. I mean, easier. Don't take me wrong. It's complex machine from the point of view of the size. And honestly, easier is not the right word, because when a fusion machine is a complex machine, if you do it smaller, the level of complexity probably is higher or equal. But you have this chance to make it faster and cheaper, because you don't need such a big volume of magnets to be into your device.
You presented at COP, and if you can summarize for our audience, but basically you put a report out there at COP which said that AI can really help, and computing can really help to accelerate this commercialization. So we're at stage one, which is fusion is a reality on Earth. And now you're saying with the AI, it can become useful because you can make it. Is that what your paper said?
That is exactly what we want to show to people who always say that fusion is still the future and so on. So no, the whole report that we released at COP is showing that the state of the art of fusion is showing that there are a number of enabling technologies that are making fusion possible. For example, this development of the 20 Tesla coils, and that artificial intelligence has the ability to help fusion to accelerate. It's a transversal tool that you can use in basically all aspects of the design operation of a fusion machine. So it's providing tools to the fusion designers, the fusion engineers that before were not existing. Many of the models that you want to test, you can test it now because you have all these capabilities. You can do a lot of simulation in silico. That means that you don't need to build 20 machines to get the parameters that you want. You can simulate it, optimize the parameters as much as possible, so you can go faster and cheaper, because you don't need to build 5 machines and test and get the information. You optimize, and instead of 5, maybe you need to build 1, and you optimize of the space of the parameters. So you can learn how the plasma behave, and you can anticipate disruption, which is a problem in particular in tokamaks. So you can control the plasma better. And as we were talking before, the plasma is the key to have fusion reactions into the machine.
This is all stunning stuff. I mean, I'm just shocked by it. But
I can tell you something. We were interviewing, and I appreciated the help of the community and the help of Amazon Web Service. We were interviewing 16 companies or entities using artificial intelligence for fusion application. It's amazing what they were telling us, how they were shortening process.
So in summary, what we're saying is that the advent of AI will make the ability for you to model things much quicker, to use less resources, so you make things not 10, do you make 1? And will it speed up the process for commercialization, in your view, to actually get us to a place where we could say, I don't know, within 5 years, we could have a fusion reactor?
If I may say, it's not something that I think is already happening. You can read the report, you can talk to the companies and the people. It's happening, it's real. And it's not that something that can happen in the future. It's happening right now.
When will I have a fusion reactor on this planet?
That is a tricky question.
In your guess?
In my guess, I think in the next decade, we will have prototypes.
Okay.
For sure. Maybe, maybe something more advanced, maybe around that. But in the next decade, we will see prototypes closer to if not like a commercial fusion power plant. That is my guess.
Okay.
Based on what I see, and all the companies release their prospect and their plans and their roadmaps and so on. So I think we will see something like a prototype in the next decade.
I haven't got a proper prop here, but I've got my cup. Now, this is the thing that everyone's, and again, you can correct all the bullshit there now today, Taylor, because it's so important. People say that the water in a cup like this, if you used it for fusion, the hydrogen in it, you could power, Madrid or London for a year or whatever. What's the reality of the potential of fusion?
Fusion have many interesting features. One of the interesting features of fusion is the power density. Fusion is very power density. Probably, I would say, to my knowledge, the most efficient source of energy in that sense. So if you compare with existing other source of energies, a kilogram of deuterium tritium, which is, as we have said, a isotope of hydrogen, is equivalent at 10 millions of kilograms of coals that you will need to burn.
Wow.
6 million kilograms of natural gas and 100 kilograms of uranium.
Oh my God.
So when you think about the need of land for building a fusion power plant, it is really limited, and you think about the availability of these hydrogen isotopes all around, and you think about the amount of power that you can deliver in this reduced space with this fuel, you can understand that mankind cannot miss the opportunity of the deployment of fusion.
If fusion happens within the next, say, 15, 20 years, it pretty much makes everything else pointless, doesn't it? Because
no. I disagree on that. And I would like to say something about if fusion happen in 15, 20 years. To make fusion happen, let's be proactive. To make fusion happen in 10, 15 years, we have reached the point that we need the adequate policies, with policies in terms of regulation, policies in terms of support to reach the point of a pilot plant, how to de-risk this technology. So governments has to push for to become a reality. And once you have that, fusion should be an important element of an energy mix.
But not the replacement. It's not the end of
I don't think fusion is the ultimate solution for everything. There are I'm very against this. No, fusion is the only thing, and then solar or wind or whatever other source of energy you have to dismantle immediately. And so I believe in an optimized energy mix. And that depends a lot about geography and the needs that you have. So you have to have options, and all these options has to be clean, okay? This is what we at the society demands. You need to be clean. You need to be no emissions. You need to be sustainable, because at the end, it needs to be sustainable. This is what fusion is offering, but it's not the only option. You need to understand that you have options, and you need to optimize that options to your needs. That probably in Madrid is different than in Helsinki and different than in South Africa. I don't know. You have to have this understanding.
I find it interesting, though. You've worked in fusion for ages. I can see you're clearly excited. You've done a brilliant job explaining it to me. Why don't you think it would be the ultimate source and just stop everything? Because if you have clean power with much less footprint, with materials that are less, not even radioactive, that can be contained, you get energy to everyone at a cheaper rate that will go out there. Why do we need to build things with concrete, such as, pylons and turbines and kind of, solar panels and all of that? Why do you say you still need the mix? I'm interested to find out.
I'm very supportive of understanding the needs and understanding the options that you have on the table. For example, hydropower is quite clean.
Yeah.
And in some places where you have rivers and you have all these jumps, you can make a really good use of that. So if you are telling me that, I think in Spain, something around 20% or 25% of the energy is coming from hydropower. If you have that source of energy, which is really clean, why do you need to replace it? You need to integrate it into your energy mix.
Uh-huh.
And maybe fusion can be the other 20, 30, 40%, because you don't need to burn any gas any longer, and so on. So let's study the territory. Let's study the needs. Don't discard anything. Open your mind with options. We need to be really strict in assessing the options. We want options that are clean, that they are sustainable. Fusion is one of them, not the only one. And when you have these clear options, you optimize. But this a priori, no, nothing, this is the only good thing. let's study.
Okay. 2050. I'm gonna 2050. Are we gonna have a nuclear power fusion power plant somewhere on the planet Earth?
Many places on the planet, I do hope. 2050 still 30 years ago, or
Yeah.
25 years from now. It's a lot of time.
Do you think there will be power plants producing?
I'm sure. And I can tell you, technologies developed not exclusively for fusion, but for other areas and for other sectors are evolving in a way that, for example, 3D printing. 3D printing materials will revolutionize fusion.
Yeah.
And now most of the fusion materials cannot be exactly 3D printing because it's a complex material, it's complicated and so, but this is now in 3, 4, 5 years, it will be available, I'm sure. So things are moving in the right direction. So by 2050, the difficult place will be not to find a fusion plant. Let's put it in that way.
I love it. What is the one barrier to this? Because the science, I love the science, and everything you said, I totally understand. But I have a feeling that the biggest barrier will be politicians, the public. They have a fear. They have a fear of nuclear power.
I can tell you something. The biggest barrier, to my understanding now, is to be able to build these pilot plants where you integrated all the technology that we have now developed and we check it how it works and we can refine things. And to build that pilot plant, you need to de-risk the financing part. This is important.
Okay.
And you need to de-risk all policy around the development and deployment of fusion power plants. This is regulation and so on. So good steps are being done in that way, in the regulation part. I mean, US, UK are following now. Germany is jumping into that, are following the right direction. Still, the financing need that push that the government should support because it's a benefit for the whole mankind.
What about the public? Public in the UK, I can tell you, I'm not sure about Spain, but there's always been this kind of mistrust. I mean, I personally think nuclear power is fantastic, but a lot of people just don't like it. They don't want to be near it. They have fears over Chernobyl and Fukushima, and they equate it to nuclear war. Completely madness. But there is this intrinsic distrust of nuclear fission. Do you feel that fusion would have the same problem?
So far, it doesn't. Fusion is considered as an advanced technology. Fusion is fusion. It's nothing to do, as I explained, with fission. It's a completely different process. It's completely different fuel. It's completely different machine and completely different principle. So it's a completely different thing. And the most recent experience that we can have in public acceptance is coming from UKA, where they were looking for a place to locate a STEP, their machine, and they were asking the whole country, and the support and the interest was huge. So people were really supported to have a fusion power plant next to their town or in their town, which is a really good thing because they found it something high-tech, which it is. It's a good thing to be developed, and you want to be part of that. You want to be part of the future, of a better future. So fusion community, we need to be transparent. We need to explain to the public. We need to make that effort. And we are moving on on that way. But I don't expect a big barrier because the public. On the opposite, people are demanding that kind of new solutions.
I love it. I'm for fusion. I need a t-shirt.
We have you in the team now.
You'll have me as your advocate. So 2050, there are fusion power plants around the world. Fusion is part of the energy mix and it is clean. That is the future you see.
That is the future I see. And this is the future that we as humans need to push for, because we need to, not the Western people, that we are having high level of standards of life. We enjoy having all the facilities around us, but there are other places like in Africa, South America in some areas, in Asia in some areas, that they are not enjoying this quality of life, this level of life. And to have a good quality of life, you need energy. And every time you need more energy. The energy demand will increase by 3 in the next decades. So we need to find how to power this. And fusion is an option. So it's a responsibility for the developed countries to develop these new sources of energies which are sustainable, which are clean, and can power all the rest of the nations.
I'm in. Sohaila, thank you so much for
My pleasure.
us. This has been a brilliant podcast. You've really helped, I think, our audience and me in particular understand this. I've always been a fan of fusion, and now I know it exists, which is great. I never thought it would. Thank you very much for your time.
Thanks to you for the invitation. Bye.
No problems. Ladies and gents, you've been listening, you've been watching. Tell us what you think about Fusion Power. Get in touch on social media. And remember, if you want to be featured, then get in touch on nethero@futurenetzero.com. I'm off to go and find myself some water. I can try some homemade fusion. See you later.
You've just heard the Net Hero podcast from FutureNetZero.com. Join us as we help you find ways to cut your carbon footprint as we head towards net zero. Subscribe and follow us on social media. FutureNetZero.com. Better business, better planet.